So there's three projects that go together, 301, 302, and 303. These are all compiling code and then examining how it's used on a Windows operating system. So you need a Windows machine with Visual Studio. Any version will do, I think. I used, the old 2017 on this. But so I'm going to do this one, stack protection, the limitations of ASLR. And I'm just going to open the instructions on a different screen so I can use this. So here we are. Here's my Windows 10 machine, and this has Visual Studio on it. So once you've got Visual Studio, you go to your Start menu to the V's, and go here, expand this, and go to Developer Command Prompt for Visual Studio, whichever version you have. And you have to do that or you won't be able to run the compiler. And then I put the code in a folder called 127A. All right. And so there's various programs that have been created here, and the instructions show you how to do it. So first you make the ESP3 program. So I'll just use Notepad, ESP3.cpp. All right, so here's what it is. Here in Notepad, let me move it over a bit. All right, so this is a C++ program, and all it does is define data, integer of 0, and then it moves the stack pointer into data. And then it prints out the data. So this just amounts to printing out on the screen the stack pointer at this point in the code. So you'll get an address on the stack frame of the main routine. All I'm trying to do is see where the main routine is located in memory. And if you run this, now there's two ways to compile it. If you compile it the normal way, which is just CL, ESP3, then what is this garbage? Exception handler used, but unwind semantics. Okay, I guess I do have to use the EHSC. I thought that was not needed, but I guess I do. I put it here, EHSC, all right? Not quite sure what it does, but it gets rid of those error messages. Okay. All right, now I have ESP3. Oops, I don't need /, that's Linux or PowerShell. ESP3, all right. So there's the stack pointer, and I run it again. It's different because I have address space layout randomization turned on, so it keeps moving around. Now you can compile it to get rid of that, and you do that with these stages. So I'll just copy this and do it again. That's fine. Copy this. All right. Oh, I probably can't copy and paste from there. Anyway, you compile it with /C, which will compile it but not link it, and then you link it with the dynamic base no switch. And if you do that, you get a version of the same program from the same source code that does not have address space layout randomization, and that's ESP4. If you run that, every time you run it, you'll get the same value because the stack is not randomly located in memory. All right. So now you can test the randomness of it, and you can do that with a Python program. And if you have the immunity debugger installed, it's installed Python 2.7, so that's what I use to do this. So this will just, for 1,000 times, run the program, ESP3. In the project, you run it 4 times just to see what happens. This is going to run it 1,000 times, so that's going to put out a lot of output. And so the way to save it is to redirect it into a file. So you run C Python 2.7 Python, and then test, and then you put the output in 10k.txt. That will be, let me get rid of the capital. There, that will put the output there. This will take about half a minute to run. It's going to run the ESP3 10,000 times, so it's going to print out all the possible values. And the interesting question here is, how random is it anyway? How likely is it to just give me this value here, the unrandomized value, 19FF24? If I take a look at it in Notepad, a 10K, see there they are, and there's 1FF7B. I'm not seeing a 19 anywhere, though. If I do edit find for 19FF, there it is, 19FF1C. It didn't find another one. So anyway, This time, none of them is exactly equal to this one, but there is a chance that you will get the same value as the unrandomized one. And how likely that is a measure of the randomness. So anyway, you just do this, and you'll see how many you get. When I did it, there were 2 of them that matched. This time I did it, there were none of them that matched exactly. And anyway, I made a flag where you just have to find the matching lines with a Python script and then run it on my data, so you'll get the expected answer, just to get a flag to see that you're doing that. And the next one is more fun, where you view memory sections. So if you run ESP4 in immunity, let me just get this set up here. So you need immunity, which is on this machine. All right, you run immunity, and let me get my instructions here. All right, then you launch ESP4, which is the non-randomized version. ESP4, okay. And run it. All right, and then view the memory. All right, and here they are. Here's the sections, 400,000. Remember, things that are not randomized always load at 400,000. There's the beginning section, the header. Then the text section is 401,000. Here's the R data and data sections at 425 and 433,000. So they're always at the same location. That's what they are. Now, if you restart it with debug restart and run and view the memory, you'll get the same answer. Because it's not randomized, of course. That's the whole point of ESP4. Always get the same answer. All right. Now, we can view them from C. If you go back to here, our Visual Studio command prompt, then there's another program here. Let's look at it. Notepad, which you make from following the instructions, mem.cpp. There. This one here is the one I showed you before. It defines an integer here, which will be in the data section. Then it gets a, this is going to be in the, on the stack, a label here. And then it, that just puts the value here in there, just to have a string in there. Then it's going to, so this is going to get in the text section is this label. This is an instruction, an assembly language instruction in the code, so that's in the text section. This is going to be on the heap. It allocates space on the heap. And then here's one on the stack. It's just going to get a pointer to this variable I, which was defined here to be in local to this routine. So that's on the stack. So now I can just print out a series, an address in a text, data, heap, and stack. That's all it does. And then it's going to print the first 9 words on the stack, so we can see the stack. So this accomplishes essentially what the immunity debugger does in C, so we can run it and see it in the command line. So if we run mem, there it is. And then it crashes because I put a break at the end of it. So I don't care about that. I'm going to close it. But here's an address in the text section, in the data section, in the heap, in the stack, and here's some values on the stack. All right. And so you can view that in immunity to understand how it works. So you load that mem in immunity. All right. And then run it. And that's why I put the breakpoint in there. It's going to hit paused. Maybe I have to run it again. Yeah, now it hits, oh, I thought it would hit the breakpoint. Debug, restart, run. There, it hit the int3 command. It vanished quickly, but it had the int3 command. So it hit the breakpoint, which is what I wanted it to do. And now I can view the memory with view memory. And I can show the running code here, and we can compare them. So here's the memory sections. And so in the text section, you have 931033, and you can see here's 931. That's in that section. Then the data section is 949, and here's the data section starting at 949. The heap is starting at 00C43, And you can see that down here, 00C4 is there, and that section is not labeled, but that is the heap section this program is using. Remember, Windows has a complicated heap structure, so there's the heap. And then the stack is 91F, and that will be here, stack of main process, 91D, and the next 3000, so 91F is there. So that's the stack. So you're seeing them. All right, and here's values on the stack, and you should be able to see that too if you go back to the CPU window. Down here is the stack, and if I bring this back and move it around so I can see it at the same time. There. Here's the one, starting here. There's 1, then there's number ending in 91, yep, 91FCFC. This is a little bit different because it printed at a different point in execution than the break that came later. For example, here's a 2, there's a loop where it prints all the words on the stack, and this one was at item 2 when it printed it. This is the break, so it was at item 9. So it is showing you the same stack, but a couple of values have changed a little bit. Here's the word here, H-E-R-E, spelled out in ASCII, which is just what I loaded in one of those variables, and so on. So you see the structure of the stack. All right. So that just shows you how it works. And now we can remove the int 3. All right, so I think we're done with immunity, and now we can just use the interactive command prompt to do this. If I do dir, okay, I got to make mem1. Okay, I didn't do these commands. I'll do them now. And I'm going to copy mem.cpp to mem1.cpp because this one crashes every time you run it with a break command, and I want to fix that. So mem1, I want to get rid of the break at the end, that line there. There. Save it and close it. And now compile it with CLEHSC mem1. Okay, and now I can run mem1.1.exe, and it prints it and it doesn't crash. And now, to see how it varies, I'm just going to animate it in a very simple way. I do a clear screen and then mem1.cpp, and what that's going to do is put it right at the top of the window. Whoops, I hit CPP. I don't want to do any of that. I want to do this, exe, there. And now if I do up arrow and press it again, it's just going to print again, and you can see what changes. So you can see the text and data sections do not move. They are not randomized. It's always the same. The next two keep moving, heap and stack. So that makes sense. The heap and the stack is where the data you put in goes largely. So these are randomized, but those are not. And now if you look on the stack, you can see the second value on the stack keeps changing. Word 1 points to an address on the stack itself. You can see here's the stack F5. This is F5. So this is a pointer to something on the stack. So of course it's going to change. This 2 is just the index I'm using to count these as I print them, so it doesn't change. This is the word here. That's always the same. The next two things here are varying. This 467, word 5, is the stack cookie. Remember, this is that random number that randomizes every time. It's not pointing to any data section. It's just a random number, and it's regenerated every time you run the program. And the last one here, 161337, that's pointing to the text section. That's the return pointer, and therefore it goes to the text section, which is not randomized, so it never changes. So the whole point of this is just so you understand what randomization is going on and what effect it will have. All right, so that's all I wanted to show you about that one. And let me see if there are comments in the Twitch, and nothing new. All right, so I'm going to stop this one.